Hi, here's your retrieval roulette for today. The only one which is a little bit questionable is, what one was it? See question 8. Show how you would calculate the resultant of the two vectors shown. If you just show how you would calculate the resultant of two perpendicular vectors for me. The rest I think are okay. Okay, so pause and get those answered now. Okay, so here's your answers. So for the one where you had to sketch the to find the resultant of two perpendicular, draw them tip to tail and use Pythagoras to figure out the resultant. And then the next one, so question 9, it must have been, was to sketch the diagram that you would use to find the internal resistance of a cell. So that is your cell with your wee internal resistance drawn on. I normally do the wee dashed line around them. You'll need to have a load resistance, which will be your variable resistor. You'll have a voltmeter in parallel with that. You'll have an ammeter in series and a switch in series. Okay, so get those marked and corrected and all the rest of it. You know the drill by now. Okay, turn in your notes to page 111. We're going to start filling in our notes on moments today. So I should say when I'm recording this, I haven't, well, it's when you're doing this work, hopefully, the past paper questions on resolving vectors. So if I need to do a wee video going over that, don't worry, I will. I'm not just neglecting it, but we'll see how you get on with that first. Okay. Right, so back to our notes. So for, well, I'm on page 111. See the stuff we were doing in moments, it's so similar to everything we did at GCSE. The only difference now is that you are going to have to use your resolving skills, because you'll have forces acting at funny angles, or the lever will be sitting at a funny angle, and you'll have to resolve either the force or the distance, one or the other. My preference generally is resolving the force, but there are definitely questions where resolving the distance is a little bit easier. Okay, so we're just going to sketch in here like what on earth we even mean whenever we are talking about moments. So a moment is just a turning effect that happens whenever you apply a force to a lever. So I've drawn here the very stereotypical lever here. We've got a wee pivot, we've got like a beam or something, and then a force is being applied to that. So this force here is going to create a turning effect, and that is a moment. So we would always talk about moments being clockwise or anti-clockwise. So if I put my pencil along this and I pivot it at the little pivot and I push it in the direction of the force, you can see that it is making the pencil turn clockwise, hopefully. So this would create a clockwise moment, right? We'll go as quick as we can through the rest of this stuff until we get onto the harder stuff. So when a force is applied to a lever, it has a turning effect. The force creates a moment about the pivot. The moment of a force about a point is defined as the product of the force and the perpendicular distance from the point to the line of action of the force, right? Basically, force multiplied by the perpendicular distance from the force to the pivot. So that's our equation. Same as GCSE, moment equals force multiplied by distance. And then we also have to fill in all the units and things, so we'll do that now. Okay, so get this written in. So F is force measured in newtons. D, I've put meters for distance because that's the most common one, and then that'll give you your moment in newton meters. Because moment's force multiplied by distance, to get this, you just multiply the units together. So if distance was in centimeters, this would be in newton centimeters. So over on 112 then we've got our first example. So a mechanic tries to remove a rusted nut from a fixed bolt using the spanner shown opposite. The spanner is of length 0.18 meters. However, when he applies his maximum force of 300 newtons, so I think my wee arrow there has disappeared. The nut does not turn. By placing the steel tube over the handle of the spanner, the length is increased to 0.27. So he applies his same maximum force of 300 and it's just loosened. So the question here is asking us what is the minimum force that would have been necessary at this original length to loosen the nut. So if we draw a wee diagram, okay, we have our force of 300 newtons, and we were told that whenever this was extended to 0.27 meters, that the moment produced by this was just enough to loosen that. So we'll calculate that. So moment's force multiplied by distance, 300 multiplied by 0.27 is 81 Newton meters. So that's the moment that is required to loosen this. So if we go back to our original situation at, what was it, 0.18 meters? This question's asking what force would have been necessary there to loosen this. So moment equals force multiplied by distance. Now we know the moment that's needed is 81. The force is what we're trying to find, and that is 0.18. So divide both sides by 0.18 and you get 450, which makes sense because it's bigger than the 300, but it's not ridiculous. Right, so on 113 we've got a few notes here on couples. Now, this, strictly speaking, is something that you do not need to know about. However, it's one of those things that can maybe come in handy in some questions. There's an example on the next page here, and I'm going to show you how to do it both as if you didn't know couples existed, and now that you do know they do exist, and then you can just pick whichever one you want to use. The only problem with couples is that I think they maybe could lead to silly mistakes. So hear me out, let's go over what they are, what on earth I'm talking about, and then you can decide whether you want to use it or not. Okay, so if you have something that has got two equal sized forces on it and they're acting in the opposite direction, but they're both rotating the object in the same direction, then they form a couple. So I don't know if what I just said there made sense, but I think this little sentence here explains it quite well. So a couple has got no resultant force, but it produces a turning effect. So if you look at the forces involved here, because these are the same size as each other, if you've got the same size force going up and the same size force going down, they're in equilibrium, they're not going to create a resultant force. However, they will create a turning effect. So a big example of this would be your hands on a steering wheel. So if you're turning your steering wheel, you're applying the same force with both hands, and they're both turning it in the same direction. So they're creating a turning effect, but there's going to be no resultant force. You don't lift your steering wheel up or lift your steering wheel down or anything like that. Now, let's add on a couple of little notes onto this. Okay, so if you add this on, just to be notes in, both forces are turning the steering wheel anti-clockwise. And then in our working out down here, I'm going to refer to the distance between these two forces as D. So mark that one. Right. So to calculate the moment of a couple, if we just do this using our normal moment, so moment equals force multiplied by distance from the pivot, then because they're both turning this anti-clockwise, the total anti-clockwise moment is going to be the moment produced by this one plus the moment produced by this one. So let's go for this one. It's going to be force multiplied by, well, the distance from this force to the pivot, which is here, is going to be a half D, right, plus the moment produced by this one, and the moment produced by this is going to be the force multiplied by the distance to the pivot, which again is half D. So if I do a wee bit of factorising here, force can come out of the bracket, and then we're left with a half D plus a half D. Oh, a half plus a half gives you 1. So we're just left with force multiplied by distance. Now, here's why it can lead to confusion, because with a couple, the equation looks the same, but this distance here means something than it does whenever you're just dealing with regular moments, like one force creating a moment or whatever. Right? So let's add on a little note here just about that, because that's my only complaint, is that we use the same letter here to mean like different things. So this here is the size of each individual force. So it's not like, oh sorry, it is not like it's both forces added together. And then this one here is the distance between the two forces. Okay, And yeah, that's the only reason I don't really like it, is because this looks exactly the same as moment equals force times distance to the pivot, but it's not, it's slightly different. So get that written in, and then let's do this little example. Right, so okay, a driver applies parallel forces, each of 15 newtons, here they are, so same line of action, same, what's the word I'm looking for? Doesn't matter. In the plane of a steering wheel in the direction shown. So this one's going up and this one is going down. The radius of the steering wheel is 200 millimeters. So from here out 200 millimeters. The driver's hand are placed in the 10 to 2 position. We're going to use this to get the angle. The left hand is at the number 10 on an imaginary clock face, and the right hand is at the number of 2. The forces are applied to the dashed line in the diagram, so like your pivot really is here, well it's here, which joins the numbers 12 and 6 on an imaginary clock face. Calculate the moment applied to the steering wheel. So if this is our pivot here, we're going to have to calculate either the component of this force which is acting perpendicular here, or the perpendicular distance to the force. Now this is one of those ones where I'm actually going to calculate the perpendicular distance as opposed to resolving the force. I just think it works out easier in this one. So I've said here, this is our first method using the normal moments method, so like as if we didn't know couples existed, how we would do this. So let's see, I'm actually going to do it for this wee one here. So if I have a force of 15 newtons acting up the way, which is this one, and I have my centre of my steering wheel, my pivot here, then because they had told us that the radius of the steering wheel was 200 millimeters, I know that that's 200 millimeters. Now, because my line of action of this force is going up this way, then I need to have the perpendicular distance to calculate the moment. So it's this distance here, which I need, which isn't 200. So to figure that out, we're going to have to figure out what this wee angle is here. So if this here, if I go back up here, if this is pointing towards 9 on the clock and this is going towards 10 on the clock, then you can figure out the angle in between, or like the numbers on the clock, and it's 30 degrees, right? So this is 30 degrees here. So this distance is going to be 200 cos 30. So distance 200 cos 30, which gets 173.2 millimeters. Then if I'm calculating the moment produced by this 15 newton force, moment is force multiplied by the perpendicular distance. The force is 15 and the perpendicular distance, this one here, is the 173.2. So that gets, what does that get me? 2598 newton millimeters. Okay, but that's only one of them. You've got two of them happening, so we need to multiply that by 2. So our total moment is 5196 newton millimeters. Okay, now once you've got that down, we will do the same question but using the couples method. Okay, so for this one, I'm really going to be redrawing a section of this wee section here, just in case you wonder what I'm at. So we've got a 15 newton force here at the 10 o'clock position and a 15 newton force here at the 2 o'clock position. Okay, now they are both 200 from this pivot here, and we just talked about earlier how we know that this angle here was 30 degrees. It's just between 9 o'clock and 10 o'clock on the clock. So see, to get the distance between these two, because if you remember using the couple method, all we have to do is multiply the size of one of the forces by the distance between the two forces. It's the same idea really, where we have to resolve. If this is 30 degrees, then this angle here is going to be 30 degrees. We've got wee alternate angles, which means that from here to here is going to be the 200 cos 30 again. And this here will be 200 cos 30 as well, because it's just a mirror image. I forgot to actually label on my original 200. I'll do it over here just because it's getting a wee bit crushed there. So this length is 200 and this length is 200, which means that our total distance between these is just these two added together, which is 346.4 millimeters from there to there. Moment equals force times distance. So the size of one of these is 15. The distance between them is 346.4, and that gets us 5196 Newton millimeters. So honestly, neither method is easier than the other. It kind of looks like this first one's got more working out, but it's just because we'd already done half the working out there for this one to get these resolved distances. So you can use either. I should say actually, I don't know how many past paper questions I've seen where couples come up, but it was in the SIA textbook, so I was too scared to not mention it, because you never know, could come in handy. Right, next little section before we just get on to examples. This is quite a short topic, it's just like these notes, examples, questions. So the next little bit is just to point out that we need to be super careful now at A level with our definitions of these things. So at GCSE, we would have really treated the centre of mass and the centre of gravity. You would have got away with mixing up the definitions, but there's slight differences in the definitions and you need to be super careful that you do them the right way around whenever you're writing them out. So let's get them in here now. So the centre of gravity is just the point that we take its weight to act. So obviously if we're talking about beams and things, they have their weight distributed throughout them, but generally we'll be talking about a uniform beam, which means that we take the weight to act at the centre point, because it'll all balance elsewhere. If it's something like a snooker cue, which is obviously not uniformly distributed, then the centre of gravity is just the point where the amount of weight is the same on both sides generally. But that's the definition that you would put down. So the point at which we take its weight to act, and then the centre of mass is the point at which we take its mass to be concentrated. Now generally they are both at exactly the same place, but there's a very rare time whenever there's not, so we need to fill that in a wee bit down here. Okay, so I actually left out this little bit here, sorry. So this means that a resultant force acting through the centre of mass would cause the object to move in a straight line, but it wouldn't cause it to rotate, because that means your distance from your pivot point is going to be 0, so you're going to have no moment. Now, for most everyday situations, centre of gravity coincides with the centre of mass. They're the same point. When would it not? If you're really close to a black hole, because the gravitational field strength is so strong, a very short distance change is going to change that gravitational force. So the weight is going to change in short distances. You'll never get asked about that. It's just for your own interest. Couple little points here. So if you have a uniform beam, uniform just means evenly distributed throughout. The centre of gravity is at its midpoint. For a metre rule, that's obviously going to be the 50 centimetre mark. Then rectangular flat sheet, which is called a lamina, so something like a bit of card, it's at its centre, and you would find that by the intersection of the two diagonals. So over the page on 116, the last key fact that we need to know for this topic. Again, you learnt this at GCSE, but in slightly less detail. So I've underlined the bits here where people tend to lose marks. So generally they could ask 3 or give 3 marks for this. 1 for saying, okay, had to pause my recording there and now I can't quite remember what I was saying. So the red lines are the bits really that are going to get you marks. So whenever an object is in rotational equilibrium, and you have to have that rotational bit in there, the sum of the clockwise moments about any point is equal to the sum of anti-clockwise moments about the same point. Everyone always forgets to put this last little bit on. So if you have if you have a lever and it's pivoted here, if you have, no, I can't figure out my brain for that. What's that? Clockwise? Yeah. So if you have a force creating a clockwise moment here and a force creating an anti-clockwise moment here, the thing's going to be balanced as That was a great demonstration. The thing is going to be balanced as long as the two moments are the same as each other. Okay, now let me just retrieve my pen and we'll carry on with the rest of this. So get that written in, and then underneath here we need to write these in as well. So if an object is in equilibrium, not just rotational equilibrium, if it's in equilibrium, there's two things that must be true. And a bunch of these questions that we're going to do make use of both of these, right? And sometimes it's easy to forget this if you're in like moment mode. So if something's in equilibrium, we already knew this, it means there's no resultant force in any direction, but it also means there's no net turning effect about any point. So this is the principle of moments, and this is just the regular something's in equilibrium bit. Right, so I'm trying to decide. I reckon today we'll just do this one example just to get us going with this, and then next lesson we will do the rest of these examples just so it's not information overload all in the one lesson. So I will be asking to see your notes filled in for this, so you better have been writing down the same stuff I've been writing down. Okay, let's look at this little example here. So we've got a seesaw and we're told it's balanced, and we have to use the principle of moments to calculate the weight W. So this unknown weight sitting here, we've got all our perpendicular distances, we've got no resolving to do, happy days. So try and get into the habit of always saying where you're taking moments about, because in this one here it's obvious we're going to take them about the pivot, but in different questions we will have to take moments about different positions to find different unknowns. So we're going to get into the habit of saying where we're taking moments about here. So I'm going to write it. I don't normally write it like this, but for our notes we will. So taking moments about the pivot. So this sentence here in my normal working out I wouldn't put in. What I would put in is just like a P for pivot, and then that wee arrow which shows I'm taking moments about that point, right? Because see, in a question where you're taking moments about multiple points, so easy to get confused, mixed up and mess up on a silly mistake. So let's keep ourselves organized. Always show you know the examiner, I said that wrong, always show the examiner that you know the principle of conservation of, or principle of moments. So I would always write anti-clockwise moments equal clockwise moments, and there'll be a mark for that. Like sometimes the first part of the question will be to state the principle of moments, and if that's the case probably there won't be a mark for writing it here, but if you haven't already stated it there's a mark for that. Now if we look up here, this is making this turn anti-clockwise, and then these two are making it turn clockwise. So instead of writing force times distance equals force times distance plus force times distance, I'm going to use little like subscripts to keep myself organized. So for anti-clockwise it's just this unknown weight here, so force times distance for W is equal to the moment created by the 300, so force times distance for this 300 force plus the force times distance for the 550. As long as you've some, like this, it doesn't have to be exactly like this, but as long as you have some way of identifying which is which. Fill in your values. So the force here is W. Distance from this one to the pivot is 1.5. This one, the force is 300. Multiplied by the distance it is to the pivot, which is 1. This one, the force is 550, and the distance it is to the pivot is 1.5. So we have 1.5 W equals 1125, which gets 750 newtons. And always have a wee check, does it make sense? 750, yeah, that does seem sensible with those other numbers and the distances involved. Okay, so that is us for today. Yeah, send me a picture of your filled in notes. All right, bye.